explanation should be mathematical. And so there should be some grand mathematical formulas, some mathematical equation that would describe everything in the universe. And Einstein sought the so-called unified theory for decades, but he never found it. String theory just may be the theory that Einstein search for the term.
Now, what kinds of problems is the scientific community faced with that leads them to come up with something like string theory? I mean, we already have studies on what the universe is made of, constituent particles and stuff, so where do we get this vibrating string?
Yeah, absolutely. So, from my initial description, it might seem like it was more of an aesthetic or philosophical motivation to try to find a unified theory, but it goes far deeper than that, because there are these two main ideas, two main pillars that support physics as we have understood it since really the middle of the 20th century, and that is quantum physics, which describes the smallest things in the elementary particles that make up matter, and Einstein's general theory of relativity, which really describes the biggest things where gravity matters, stars, galaxies, black holes, and the entire universe. And the problem is that even though quantum mechanics works incredibly well in the micro domain, and general relativity works incredibly well in the macro domain, whenever you try to put the two mathematical theories together, it breaks down. When you do any calculation that blends the math of quantum mechanics and the math of general relativity, you get one single answer, and that answer is infinity. And infinity might sound, well, that's kind of, cool and poetic sounding, but it's nonsensical in the context of physics. There's no quantity that you can measure that's ever infinity. So infinity is a diagnostic, which basically the mathematics uses to kind of grab us by the lapels and slap us in the face and say, you are doing something wrong. You've got to find a new description that puts quantum mechanics and general relativity together. And that is what string theory does, at least in principle on paper. I need to stress that. This is not a tested theory. We don't know if it's correct, but mathematically for the first time, it does show a way of bridging the gap between these two theories.
Does this tell us that of general relativity and quantum mechanics, at least one of them is sort of wrong? People often talk about general relativity as coming along to replace Isaac Newton's understanding of gravity. They say Newton was kind of almost there, but ultimately he was wrong. Is that the same approach we need to take to something like general relativity as well?
It is, but I would caution to see it in that historical context that you just made reference to, because it's a little strong to say that Newton was wrong. I would say that any physical theory that we ever write down is meant to describe the universe in a certain domain. And when we gain better equipment and when we make progress, we try to extend the domain of applicability of our understanding. And when we do that, we almost always find that the ideas from the earlier generation, yes, they really work in the original domain, but when you go beyond that domain, you need to update them, you need to replace them. So Newton did a wonderful job at describing the orbits of the planets. General relativity comes along and says, well, actually, a little bit further than just the orbits of planets. You want to understand more extreme environments like black holes, then you need these new ideas of the general theory of relativity. And that is indeed the process that we feel we're likely recapitulating now. Because when you try to put quantum mechanics and general relativity together, you do find, at least in the string theoretic context, that general relativity has to yield to additional terms, additional mathematical constructs that Einstein himself did not write down. And so, yes, as we try to go beyond even the domain that Einstein successfully described, when we try to put quantum modified. Now, it could also be that quantum mechanics gets modified. This is an idea that people are talking about today. So that would again fit into exactly the same template. Earlier ideas, when you try to go further, require new concepts, new ideas that have to be modified.
Do you think that there is a sentimentality in physics where people kind of want to cling on to these famous revolutionary ideas? Because, as well as the questions, theory, they're exciting, familiar with them. And so when you're faced with something that causes you to abandon something so familiar, I think there is a psychological barrier for a lot of people.
I think it's really depending which physicist you're talking about. So are there some in the history of physics where you can find reasonable evidence that they were reluctant to take the new step because they were so tied to the old way of looking at things? Yes, you can even in some way say that about Einstein in some ways. When quantum mechanics came along and was suggesting that the best you could ever do is predict the likelihood, the probability of one or another outcome, very different from the classical perspective that Einstein was used to, where you tell Einstein how things are today, and Einstein will tell you how they will be tomorrow with 100% certainty coming from the mathematical equations. When quantum mechanics began to chip away at that picture, yes, is there some evidence that Einstein resisted it? Absolutely. But I would say that the dominant perspective of most physicists, including